Okay, today we are going to look at some of the papers that you guys have chosen. I think they were, for the most part, very, very good and interesting papers. And I think that if you've worked it out, we have 1, 2, 3, we have 6 people. We have 2 periods to do it. So I'm thinking about, and I hope you plan for this. If it's shorter, it's fine. If it's longer, we'll live. But I'm thinking around 20 minutes and plus 5 minutes for Q&A, if anybody has any Q&A, okay? So with that, let me put up my screen here. And you can see this is the spreadsheet that we had. And I think we'll just go down in terms of the sign up. Now, everybody, is that too small? Can you make out that font? I know it's, okay, that's good. We'll quit with Ingrid and Eyeball. This, by the way, is one of my fictitious aliases, and her real name is Miss Ingrid Nyball. See, Ingrid Nyball, missing an eyeball. Okay, so there's a website called missingandeyeball.com if you ever want to go there. So let's go ahead and start, and Sam, will start with you. And on this list, you can see everybody has access to it, is the link to the paper. And so you can link to the paper. So with that, Sam, I will stop sharing. I will give everybody the ability to share the screen and ask that you go ahead and go first. Okay, Sam, it's up to you.
Okay, so my paper dealt with swarm task allocation. And again, the paper's on the sheet if you're interested in looking at it. So a little bit of an overview here. So it studies a model of social insects, which are extremely successful. And again, this is closely tied to swarm intelligence. And one of the things that social insects have that is not well understood is task allocation, and how, swarm has, 25 different tasks, and they have to allocate a certain number of insects to accomplish those tasks in order to get everything accomplished that needs to be done in order for the hive to thrive. And so there are obvious applications to swarm intelligence here. If you have a bunch of swarm units and you have several different tasks that they need to accomplish, but you're not interested in a centralized task allocation method, then this sort of modeling will be helpful in determining that and making a successful swarm. So this paper appeals a lot to economics and game theory, which I actually had the pleasure of taking a few economics courses in undergrad. And so I've always enjoyed the game theory kind of side of economics. So there's a lot of cost benefit analysis that goes on here. So you just compare the costs and the benefits. And if the costs are greater than the benefits, then that's not a good choice. If the benefits are greater, that's a good choice. And then you can compare between choices, just the relative ratio of cost to benefit. Another thing is rationality. So the assumption here is that a rational decision maker will choose an action which has a higher benefit to cost ratio. So if there are 2 actions and one has a slightly higher benefit to cost ratio, then they will choose that one. That's an assumption made in game. Another thing that'll be important here is diminishing marginal returns. So this is if you devote a whole lot of resources to a single task, you're not going to get as much benefit per resource unit the more you put into it. So this kind of diminishing marginal returns is very important. Yes, we'll talk about that quite a bit. So here's the application of game theory to social insects. So each of these insects is going to be concerned with the benefit of the hive. And so in game theory, each individual is attempting to maximize their own payoff, their own payout, without concern for other players. But in this particular sense, the hive's benefit is viewed as an individual benefit to the swarm unit. So if the swarm unit is able to produce some kind of good for the hive, then they will see that as a beneficial individual gain, and so they will prioritize that. And so that equation on the right, pi would be your total outcome, and then B would be your benefit, and then you'd subtract off your cost. So the higher the benefit and the lower the cost, the better the overall outcome. So another thing that's mentioned in this paper is that each insect does not have an omniscient view of the hive's total performance, but they do have some metrics to tell how the hive is doing overall. So an example here would be how often a unit encounters another unit which is hungry. So if you have an insect in a swarm, if he encounters a bunch of hungry insects at a high frequency, he's going to assume that the hive is low on food. And that's kind of the idea here, is that they don't have an omniscient view of everything, but they do have their own individual view of how the hive is doing. As discussed in this paper, just with this knowledge, and this is knowledge of only perceived benefit to the individual, an emergent property of this game theory trying to maximize hive benefit is that the hive as a whole has its needs met by the individuals, even though they're not directly aware of like the hive's food supply, for example.
Sam, is the subscript I denote individual
swarm
yes. units?
Yes, good question. Yes, the I is for an individual swarm unit or insect, yes. And so the total hive benefit would be the sum of all the individual outcomes. So you'd sum up all the benefits, subtract all the costs. Yes, good question. All right, so a little bit into the model of the actual swarm. So there are a couple of different types of tasks. There are the necessary tasks, which are deemed or are called T. Those are the set of tasks that are necessary. It's named T after the thermoregulation term, which is a necessary thing for a hive. So a few important features of these necessary tasks is that there is a kind of a happy medium. In biology, we call this homeostasis. Like in your body temperature, if it's too high, that's a problem. If it's too low, that's a problem. But if it's in that optimal range, then no more action required. You're in homeostasis. You're ready to live, I suppose. And so we would call this concave, which means if you put in a whole bunch of worker effort into this task, it will eventually start declining in its benefit. And so like if you have all of your insects warming your hive, it may become too hot. So there's a kind of a middle ground here for how many units are supposed to be working on it. Then there are some maximization tasks, F, which F stands for foraging. So these are convex. This is like gathering food. The more food you gather, the better. So there's no kind of concave behavior. It's just the more the better. But we have to kind of figure out how many people to allocate to each task. This is going to be into a little bit of convention used by the paper. X sub I is an individual's effort level spent on thermoregulation tasks. So this is between 0 and 1. So if their X sub I is 0, then they spend all of their time foraging and they spend none of their time thermoregulating. This isn't super important to keep straight, but just so you know, they do have this this kind of metric for how you're allocating effort. And then the effort spent on the F task would be the complement of that. Okay. Oh, another thing they take into account is task learning. So if one insect does, say, a foraging task for a day and hasn't done any thermoregulation, they would probably have a higher efficiency at the tasks that they have done for a while. So we're assuming some kind of passive task learning, and so they become more efficient at it over time, which does yield itself more to specialization. Okay. So a little bit about the cost benefit analysis. The benefits here are going to be multiplicative. So in this equation here, the sub T is for the thermoregulation tasks, the necessary ones, the F for the foraging, the non-necessary but still good tasks. And so we're multiplying them because we don't want to neglect one of them. So if we have all of our benefit in, say, the foraging task and none in the thermoregulation task, that would be a failure because thermoregulation would fail and the hive would die. And so we're multiplying the benefits for those. And all the costs are additive. So whether you spend all of your effort on foraging or all of your effort on thermoregulation, we're just going to sum those costs. And so it's kind of a linear addition there of cost. Next thing, the benefits are shared, but the costs are individual. So the benefit there, the B term, is divided by n, which is going to be your number of insects. In the paper, they actually divide it into subcategories of subgroups inside your swarm, but the concept is still the same, that it's shared among your fellow swarm units. Okay. All right, so a couple of environmental factors that go into their modeling. So B is going to be the benefit versus cost of foraging. So this is essentially going to mean how easy is your environment. If you're in a super harsh environment where you forage for 8 hours and you find 1 acorn or something, I don't think you eat acorns, but so the idea here is if you have a really high B parameter, then it'd be really easy for you to go find food. Whereas if you had a really low B parameter, you could spend a long time but not really find anything. So your benefit is pretty low. Another factor here is going to be R, which is the relative cost of foraging versus the other tasks. So this is going to be a comparison between the two types of tasks. So if R is really high, that means that the thermoregulation tasks are really expensive, but the foraging is really cheap, and vice versa. So these are just some parameters that they list and use to kind of test different scenarios of their hive. So here are a few graphs, and these kind of show the effects of these environmental parameters. So the graph on the left is going to be kind of looking into the B term. So for very high B values, which means that your environment is very conducive to gathering food, for example, you'll be able to get a higher benefit out of it. So if you see that dotted green line, you're able to get a much higher benefit per person, because when one insect goes out to find food, they'll find a bunch. And so they're able to get a higher benefit out of it. And also is considered on the left plot is the number of people in your hive. If you have a large hive, you may want to consider allocating more people because you have more people to do foraging. Whereas if you see that solid green line on the bottom left, there are not many people in that hive, so the maximum benefit on that curve is pretty low. You'd want to allocate like 2 or 3 insects to that task. And then on the right, this one is a little harder to interpret, but it goes through the relative benefit versus cost of the T tasks versus the F tasks. So on the x-axis here is how much effort you put into your thermoregulation tasks. And it just shows you that if some tasks are more expensive than others, then you may have a higher cost in investing in those tasks rather than. And feel free to stop.
By the way, boy, all sorts of interesting thoughts here. Isn't indeed this relative cost of foraging versus performing a task something like reinforcement learning?
Yes, they do talk about reinforcement learning quite a bit. I'll cover that a little bit later.
Oh, that's coming up. Okay.
Yes, reinforcement learning is applicable. Yes.
Okay, please go ahead.
Okay, so first we'll talk about a couple of different types of learning that they looked into. One is individual. So you start with a strategy. You just pick an amount of your time to spend foraging and an amount of your time to spend thermoregulating. And you have a small chance to try a new strategy at random. And you're more likely to choose strategies that are kind of closer to what your strategy is. And then when you choose a new strategy, if your overall perceived benefit to the hive is greater, then you'll switch to that new task. Otherwise, you'll switch back to your original. So you'll kind of test out new tasks and choose which one is best. Your availability of history to look back on is limited to your own personal tasks. So you only have knowledge of the tasks that you have completed, and that's the only history that you have.
I'm hoping I'm not stepping on your presentation, but doesn't this remind you of particle swarm? There's kind of the local best, and then there's the global best, and you are balancing between the two in some way.
Yes, that's true. Except in this particular case, they have no knowledge of the global best. They only have knowledge of their own personal best. Yeah, in individual learning, it does talk about social learning. We'll get into that in just a second. But for individual learning, you're only able to see your own maximum. You're not able to see the global. Okay, so yeah, this is very similar to reinforcement learning. So if you're familiar with multi-arm bandits, this is pretty much exactly the epsilon greedy method, where you choose, there's a small chance for you to choose a different bandit, and then if it's better, you switch. Nice. Let's do that in there. So next up, another type of learning that they investigated is social learning. So here you have you start with a strategy, and you have a chance to consider how one of your other swarm units, one of your peers, is doing. So you're able to, in this learning environment, you're able to deduce how well their strategy is going. You're able to gather information on the benefit that they are producing to the hive. There's a chance here to choose their strategy. If the peer strategy is very effective, you have a high chance of choosing it. If it is less effective, you have a smaller chance to select it. So the idea here is to choose the most successful options with a higher probability. Okay, so now that all the kind of definitions are out of the way, here are some results. So this graph is a little complicated. So let me just move my Zoom thing over there. Okay. So the primary graph here is going to be this display on the right. So the X and Y axes here are B and R. So B, again, is going to be kind of how difficult your environment is. And R is going to be the relative cost from one task to another. So here, if B is really small, if you're in a very harsh environment, there are many of these environments where the hive just dies. There's not enough, you're not able to get enough benefit out of your tasks because that environment is just too harsh, just not able to survive. Then an interesting trend we see here is that as B increases, we enter a region of strong specialization. So this is a region where the environment is pretty harsh. So the hive is definitely constrained, feeling the effects of the environment, but they're also able to survive and get a higher benefit than their cost. And then as B moves even greater, we can see that there's a stage of weak specialization where everything is plentiful. It is not as important to kind of optimize your behavior as much. And so it is very weakly specialized. And so how this is interpreted in those other graphs are, this is kind of how many of the swarm units are choosing each task. So in the inviable regions, they all choose one task and then the hive fails. In the strong specialization, we can see about half of them choose an X value, which is really high, which means that they are foraging. I can't remember which one's which, but essentially half of them are foraging all the time and half of them are thermoregulating all the time. So we have this very strong specialization where not many of them are doing half and half. Whereas in the very plentiful environment, you see a lot of everybody's doing half and half. So they're not attempting to specialize as much. These are just kind of the results they saw. This is for individual learning. These graphs are for social learning. So the same kind of thing here. You can see that inviable region on the left for very low B values. And we also see this strong versus weak specialization. And you can also see that the demarcation between the regions is not as clear. And this kind of is because for social learning, there's kind of more of a stochastic element than in the individual learning, because depending on where the hive started in all their effort allocations, they might not have found the best solution, and they're just looking at each other's benefits and choosing the best of those. So they may not find.
Were these plots derived by modeling?
Yes. They simulated
by kind of a Monte Carlo sort of performance.
Yes. Yep. That is correct. Okay.
And what is B again?
So B is kind of how harsh the environment is. Low B values means that the environment is very harsh, not super suitable to life. But if for super high B values, that's like Garden of Eden type. Everything's plentiful. You don't really need to worry. There's just so much material.
Okay, and R is
going to be the relative cost between the necessary and the unnecessary tasks. So if, say, the necessary tasks have a lot of cost, then but you still need to do them because they're necessary. You might need to allocate more people to do it because it needs to get done, but it requires more people. And so that's just kind of that thing. Okay. Also an interesting thing to note, looking back and forth on the diagrams, there are some environments that individual learning is able to produce a viable colony, where in social learning, it is inviable. So you can see that blue region, or whatever color that is on the left, covers more of the graph. Sorry. So social learning is not quite as good at finding the total optimum, because they're just concerned with viewing each other's performance rather than exploring previously unexplored performances. Okay, so a little bit about emergence. So a couple of cases yield strong specialization. If you have very large colonies, they're more likely to specialize. And if you have harsh environments, but not harsh enough that the colony is inviable, you'll have some strong specialization. Weak specialization occurs if you have small colonies. So in small colonies, there's not really enough for you to go whole ham on thermoregulation, for example. You probably need to balance, I need to do some thermoregulation, some foraging, because there's just not enough people for you to go for to fully specialize. Also, in abundant environments, there's weak specialization, because there's just not much of a need to have that kind of divide. So they essentially just end up where they end up, which just happens to be a shared effort allocation. Okay, so they did also do a little bit of environmental change. So let's say that you start in a very abundant environment, but then conditions change, you move to a very harsh environment. Individual learning is able to adapt very well, because they're not limited to what their peers have been doing. They're able to kind of explore on their own, what if I did this, what if I did this, and find what does better. Social learning is not quite as good at adapting to environmental change. And that's just a result that they found. Okay, so we'll get into something called the Price of Anarchy, which is actually coined in the paper. Well, I don't think it's coined in the paper, but it's referenced by name in the paper. So the Price of Anarchy is a trade-off between investing resources in organization and incurring a cost based on not specializing. So in the simulation results, in very abundant environments, there is enough benefit to pay for this Price of Anarchy. So when the environment is very plentiful, there is enough to go around so that anarchy is able to be funded. There's enough funding for anarchy. But in more harsh environments that are more constrained, the Price of Anarchy is too high, and so specialization occurs, and the swarms are able to do that individually. So this relates a little bit to biology in a couple of respects. Firstly, if you look at the human body, for example, you have a bunch of very specialized organs. So, the heart does its one job and nothing else. The lungs do its one job and nothing else. And so we see this specialization occur in order to make life happen. Another example would be in very simple organisms like crustaceans, they do not have a circulatory system. It's not really closed. They just have an open cavity and blood just kind of flows. And if it's oxygenated, fine. If it's not, whatever. And so that is able to work in very simple organisms because the price of organization is greater than the price of anarchy. So the organism is essentially small enough for them to survive with no organization or little organization. Whereas when you get to a human, the price of organization is low enough that the price of anarchy is too high. And so it is better to specialize very highly rather than pay the price of anarchy. And so this also goes a little bit, I think, with computer science, and they mentioned it. If you're writing a very short program that only does one thing and you're not worried about robustness, for example, then you may not be as concerned with breaking things into functions and classes and being super organized, because it's a one-time thing, and doing all that organization may be too expensive. But on the flip side, if you're doing a very large project with maybe lots of people involved that does a lot of things, you're very motivated to make it very modular, very easy to understand, break it up into functions and whatnot. So those are a couple of applications of that. So again, swarm intelligence. If you have a swarm with multiple roles, you can apply these concepts to allocate tasks. and you can use these modeling techniques. Game theory primarily is used. And with these modeling techniques, you can have some insights into what your swarm may do in a certain environment without actually having to do it, because you might have good modeling to be able to predict that. Excuse me. And that's it. If there are any questions, I'd be happy to field those.
Okay, anybody have any questions? I was reminded in here, Sam, a lot of reinforcement learning, where you had the trade-off between, for example, the anarchy and what was the trade-off with?
They didn't coin it, but I talked about the price of organization.
Okay.
Effort needed to organize.
Yeah, unfortunately, we did not talk about reinforcement learning in this class, but I'm sure that those of you that have had Professor Rivas's course or Professor Dong's course have talked about reinforcement learning. So anyway, yeah, I found a lot of interesting analogies in here. It's kind of like that this happens in nature, and we're kind of discovering it. The other thing, I just did an interview with a guy named Eric Castle, who wrote this fascinating book called Animal Algorithms. And he talks about the innate algorithms that animals, including human beings, are born with. Like the human being is born with a certain affinity for being able to recognize faces. A baby will immediately go for the breast. There are these certain algorithms that we have. And certainly in these social insects, we have these algorithms, and they're not really simple. And the question is where do these algorithms come from? Are they evolutionary in scope, or what is the source of them? So it seems to me that one of the most difficult things to evolve is like a computer program, if you will, an algorithm. And so I would think that would be problematic for an evolutionary explanation, although I'm sure that there are things which are going out there that do talk about an evolutionary development. The cost benefit also reminded me of fuzzy conjunction and fuzzy disjunction. I think that one could use the product, instead use a conjunctive, and with the other one, the benefit, let's say, I think it was the cost that was additive. So that would be like an or, and the other one was the benefit, which was kind of an and so there was this relationship here. The other thing that always bothers me is when we put together models and the results are only as good as the models and the relationship to reality. Did they go into any relationship with reality in this, other than to say, it did this, and we kind of see this in a way?
So they did talk about how they did not intend to model all aspects of a swarm, and so they did mention that they chose a few specific properties of task allocation and studied those specifically. So yeah, they definitely mentioned that they bit off a few things and then studied those. So I don't think they would claim to be able to model an entire swarm accurately with all its bells and whistles.
Well, it still would be nice if that piece of the model was applicable to a specific swarm. So
right.
The other thing, did they mention were engineers any application to reduction to practice? For example, I could think of things such as crowd control, organizational control, where you have a swarm of people and you would like to have the swarm of people be productive in some sort of way. Was that mentioned at all?
No, they mentioned that they just are proposing a method of modeling for further study. So I don't think they proposed any reduction of practice yet.
Yeah, it does turn out the swarm intelligence has been applied to things such as crowd control, and where you avoid, for example, a fire in a theater and all of these people, panic and do stuff. And you can make some very interesting observations and models concerning that. Okay, thank you, Sam. Any last question at all?
I have kind of a quick one. What was sort of the barrier for modeling this analytically?
That's a good question.
Like, did they?
I don't know.
It looks like kind of the epsilon greedy approach might be hard to model with a bunch of agents, but I was
Yep.
curious if they tried something like Thompson sampling, which is another.
I don't know that. I do know that they'd use kind of a Monte Carlo empirical test just with a lot of data points. But I no, I don't know off the top of my head.
Thompson sampling applied to reinforcement learning. Is that what you're talking about, Colin?
Yeah. So a while ago, I was working I was doing an internship for a company, and we were working on multi-armed bandit models, and basically trying to predict the behavior of an ensemble of bandits. And Thompson sampling was kind of a Bayesian approach to model how an ensemble of these would behave.
Right.
But it ends up reducing to Monte Carlo sampling, but it gives you kind of a better, I don't know, mathematical perspective on it.
Well, I think that, yeah, some of these things can be modeled, but once you get away from the linear, from the x dot is equal to ax plus bu sort of modeling, you get into challenges as far as the analytic tractability of it. That's my experience. So I think that this is probably an attempt to get to that higher level, which is above and beyond just a linear or even a pseudo linear sort of approach of doing things. So, okay, thank you, Sam. Let's go ahead and move on. Then, and by the way, if we do run over and you have to leave, that's fine. I'm going to stay here until the last light is turned out. Okay, so I'll be here until the end. But if you have to leave, that's fine. Okay, Colin, we're all ready for a very interesting presentation on every model learned by gradient descent is approximately a kernel method. And I'm sure you're going to keep this exciting and everybody on the edge of their toes, right? Edge of their seats, not the edge of their toes, the edge of their seats.
All right, I will go ahead and share my screen.
Okay.
Let's see. All right, are you able to see this?
Yes. Now we did not go over kernel machines in the class, so we're touching on things that we haven't formally covered, but hopefully you can provide a sufficient runway for everybody to understand. Please go ahead, Colin.
Right. So yeah, I'm going to be just presenting on kernel machines and models trained by gradient descent and some of the connections that were found between the two by the paper that you can find linked on the spreadsheet. So a bit of a disclaimer. This is going to be sort of a two-part presentation. First part is going to be what actually are kernel machines, because we didn't really talk about it, so I wanted to make sure we could give an introduction to that. And then the second part is going to be talking about this paper by Pedro Domingos that talked about drawing some pretty interesting comparisons between models trained by gradient descent and kernel machines. So kind of about this presentation, I'm actually presenting this out of a Jupyter notebook. So there's a fun little widget that lets you export a notebook to slides. And so there's actually some runnable code in this presentation that's just going to give you some examples of how you can actually apply this in your engineering projects. Feel free to copy and paste this code. No need to attribute me or anything. But these are kind of the dependencies that I'll be using. Yeah, I'm going to be kind of supporting some of these key background ideas with functional Python code that you can run and use yourself. So
for the record, I understand none of what that code says, so but that's okay. Maybe other people will. Good.
Yeah, this is just saying these are all the packages that you have to import. Primarily, I'm going to be using sklearn, but yeah, I'll talk about that a little bit. So first, let's talk about what are kernel machines. So kernel machines are a type of classical unsupervised machine learning model in which we sort of use a notion of similarity between the elements of a data set in order to perform classification. So I think we did something kind of reminiscent of kernel machines with Dr. Marx's fuzzy similarity measures. As we'll see later on, actually using the dot product is sort of the most intuitive notion of similarity. And in fact, mathematically, this similarity takes the form of an inner product that is evaluated in some high dimensional space. And the motivation for sort of using this notion of similarity as an inner product comes from a result known as Cover's theorem, which we'll talk about. in the coming slides, we're just going to look at just a few illustrative examples of Cover's theorem and what it means and how it's significant in the context of kernel machines. So you all have probably used a linear classifier before. It's just a model that takes this form where y, which is our prediction value, that's either plus or minus 1, is taken to be the sign of some weight value, some weight vector transposed times x, where x is sort of our input value that we're trying to predict. So y hat is our prediction value. It's positive or negative. W is the weight vector, and x is some feature vector that we also include a bias term so that we can sort of shift our linear classifier left and right. And this form allows us to basically draw a line between, whether it's sumo wrestlers and basketball players or whatever our data set is. And sometimes this is referred to as a linear perceptron model, going back to some of Minsky's early work in these kinds of models. So by inspection, we can kind of see that a linear classifier would work well for this kind of a data set, where we have just two features, x1 and x2, and we see that all of the blue values, which are the positive 1 features, are down here, and the orange features, which are the negative 1 features, are up in the right-hand side. And so here's just sort of an illustration of how you can use a linear support vector classifier, which is really a fancy term for just a W transpose X model. And here's just some Python code. I won't linger on it, but you can look at it later. That basically just classifies this data and fits the data set to a linear classifier. However, if we take a look at this data set right here, it's unfortunately not separable by a linear classifier. We can kind of see that if we try to draw a line between them, there's always going to be some blue points on one side that should be on the other side, and some orange points that are unfortunately on the side that they don't need to be on. But we do kind of see that maybe if we were to draw a circle around this region here, we could maybe say all of the positive predicted classes are those that lie within the circle, and the negative ones are the ones that lie outside of it. So we can kind of see that linear separating the data points in the given 2D space is not possible. However, we claim it's possible if we separate these points using a second-degree polynomial transform, which we'll denote by this capital phi. So this here, we can think of phi as taking real values in R3 to R6, given by sort of this mapping here. Notice that there's a 1 here. This sort of corresponds to the bias term. Again, in the linear classifier case, we include that bias term so that we can shift our classifier left or right. It doesn't necessarily have to go through the origin. So if we have two variables, x1 and x2, those map to basically all the possible polynomial terms we can construct. So we have an x1, x2, x1 squared, x2 squared, and then the product of x1 and x2. And so by inspection, if we kind of were to go back to the previous data set, this classifier would sort of serve to separate our data, where we compute the radius squared as x1 squared plus x2 squared, and subtract that from 1/4, and that is our classifier model. So yeah, as we'll see later, this transformation phi actually corresponds to a second-degree polynomial kernel. And we'll talk about what a kernel is in a second. And so here's just our support vector classifier. This time we're using sklearn's SVC, which is a support vector classifier. We use a polynomial kernel and set the degree to be 2. And we see that indeed we can actually create an ellipse that separates our negative data points from our positive data points. All right, so now let's actually talk about Cover's theorem. So this theorem was sort of first proposed by Thomas M. Cover in 1965 and has a plethora of generalizations. But roughly stated, the theorem says that a complex pattern classification problem, if cast in a high-dimensional space non-linearly, is more likely to be linearly separable than in a low-dimensional space, provided that the space is not densely populated. So in sort of the most general form of this theorem, it says that any finite topological data set with a finite number of classes in a topological space with countably large dimension is linearly separable and embedding within a countably larger space. So that sounded like a lot of math terms. Essentially what this says is that if we take a data set and we project it into a much larger, higher dimensional space, it's much more likely that we can draw a line or a hyperplane that separates the positive instances from the negative instances and classifies our data set correctly. And so here's an example of an interesting kind of embedding. This is going to be a countably infinite embedding. We're going to take a finite dimensional data set and explode it into an infinite dimensional space, at which point it would be linearly separable. So consider this data set where we have a bunch of positive data points that are sort of clustered in a collection of islands. So you can see we have all the negative data points are sort of scattered throughout the plane, but then we have small clusters of these positive data points. So we can kind of see that clearly this won't work well with a linear model, and probably not really well with like a second order polynomial transform. But sort of one intuitive approach we could use to classify this data is to use a nearest neighbor model, where we classify data points as positive only if the sum of the negative exponentially weighted distance of points that we want to classify to known positive data points exceeds a given threshold t. So we're basically saying, okay, if I have a data point that I want to classify, I basically find, okay, which data point that I've seen before is closest to that one. And that's sort of modeled by this exponentially weighted sum of distances to known data points. And then I can just sort of use this nearest neighbor comparison to give me a decent prediction.
Now, is the X super plus, is that in some way denoting a cluster of points close together?
So here, yeah, so here the X plus would be the set of positive data points, the ones that are that have the +1 label to them. So this just says if I have an unknown data point X, I basically compute this exponentially weighted distance relative to all of the known positive data points.
And so this puts a little hump around every data point, right?
Essentially, yeah. Just sometimes this is called a radial basis function or Gaussian kernel. We'll get into that in a second. But yeah, it just puts a little Gaussian hump at each data point. So if we were to use this fact that we compute the norm squared, or the magnitude squared of the difference between any vectors, which we do up here, we can kind of separate it out into this summation of a dot a minus 2a dot b plus b dot b. And sort of using that, this simplifies to this down here, which is just a product of exponents. And this is essentially, if we were to look at sort of how each entry in these vectors behaves, this is sort of a product of sort of entry-wise exponents like this, e to the power a sub I times b sub I, where these are the ith entries of the dot product a times b, each of which we can expand using a Taylor series and write it as sort of this complicated inner product here that goes on to infinity. And then we can sort of expand this and separate out the a terms from the b terms, and we get sort of this dot product here. Essentially, we're really just computing an infinite dimensional polynomial transform. And this is sort of well defined because of this Taylor series expansion here. So hence, we can actually write this classifier in the form of sine of w transpose phi of x, where phi is proportional to this infinite degree polynomial transform. So in fact, we can perform this sort of nearest neighbor classifier by sort of exploding our data set into an infinite dimensional space and computing a linear separator in that infinite dimensional space. But obviously, it's not practical to do that. This is more of a, gives you a sort of a theoretical insight. So a linear classifier with respect to some embedding phi takes this form, W transpose applied to this embedding phi of x. And sort of fitting a data set to this classifier is essentially a convex optimization problem in this embedding phi. And I won't go into the details, but in the theory of convex optimization, this is what's called a primal formulation of a problem. And we can actually convert this problem to its either strong or weakly equivalent dual formulation by introducing a kernel function k, which is essentially just this inner product of the embedded values of any two feature vectors a and b. So all a kernel function is just an inner product and some higher dimensional embedding. So there are sort of two interpretations here that we're working with. One is that a kernel function denotes some notion of similarity, and the second is that it's really under the hood, just an inner product in a high dimensional space. So as in the previous example with the nearest neighbor classifier, it's clearly much easier to compute the kernel function than it is to evaluate this infinite dimensional inner product. So this is where kernel functions can actually be much more useful than computing linear classifications. All right, so now let's actually talk about what a kernel machine is. A kernel machine classifier with some kernel k of a and b has this form right here, where now what we're doing is computing a sum of this kernel applied to whatever value we want to classify, and each of the elements in our data set, which are denoted by these x sub I, weighted by some constant alpha and the actual classification value of that corresponding data point, y sub I. So again, yeah, y hat is the predicted class of x prime. And this set of pairs is sort of the set of data with known labels and classes. And all of these alphas are essentially scalar weights. And by the way, these alpha values actually correspond to sort of the Lagrange multipliers of these kernel inner products. If you've ever heard of Lagrange multipliers, that's sort of where these values come in. So a kernel function, again, can just be thought of as a similarity function. And what k actually does is sort of implicitly compute this inner product without actually computing this projection into some much higher dimensional space.
So are the alphas computable then, the Lagrange multipliers?
They are, yeah. I'm not going to go into the details of how you actually train a kernel machine. It's a little bit more complicated. But yeah, going back like a couple of slides, we talked about this primal dual optimization problem correspondence.
Right.
If you think of like the primal problem as like finding the maximum of a function, the dual formulation is like finding the regions where sort of the gradient of the level curves is sort of 0, if that makes sense. It's setting the derivative equal to 0. And these alpha sub i's are essentially the Lagrange multipliers or derivatives. So sort of due to this primal dual optimization correspondence, an optimally fitted kernel machine is equivalent to an optimally fitted linear classifier with some weight vector w under some higher dimensional embedding phi. Given certain regularity conditions, these two models are actually equivalent. But the good news is that we don't necessarily have to compute this higher dimensional embedding if we know what the kernel function is. So although these models are equivalent, there are sort of pros and cons to each. And so, for example, linear classifiers only require the storage of this w weight vector, but are infeasible for infinite dimensional projections phi, whereas kernel machines can learn many nonlinear classifications of data, such as our nearest neighbor example. But the model is actually dependent on the data set and set of weights corresponding to each data element. So unfortunately, with kernel machines, we actually have to carry around our entire data set with the model. So that's a bit of a price to pay for nonlinearity. But actually, as we'll find out, we don't have to carry around the entire data set with our model. Although kernel machines appear to require this entire data set to make inferences, this actually isn't always the case. In fact, many of the, I'm sorry, that should be an alpha sub I. Many of the alpha sub I weight vectors end up as 0 vectors, especially when the kernel function is relatively simple. So if we go back to this definition here, many of these alpha sub i's, the optimal values actually turn out to be 0 for several elements in our data set, which means they effectively contribute nothing to our model. So we can basically throw those in the trash can and only keep track of the data elements that have non-zero alpha sub I values. And these data points that have these non-zero alpha sub I weights are called support vectors. Kernel machines that only retain these support vectors are what are called support vector machines, or SVMs. So intuitively, these support vectors we can kind of think of as the data points that are closest to our decision boundary. So in the linear case, if we have W transpose X equal to 0, our support vectors are going to be these data points, both in the positive and negative classes, that are sort of closest to our decision boundary. So if we only really know sort of the points that we need to keep track of, we can completely ignore all of the other points and only keep track of, say, these 5 points in order to make a meaningful decision. And so here's just an example of a support vector machine. sklearn calls them support vector classifiers, or SVCs. This is applied to that data set we saw earlier with all of the isolated islands. And here we used our RBF, which is the same thing as a nearest neighbor kernel, with sort of the radius of that kernel set to 30. So we can see that this actually produces a pretty good nonlinear model for our data set. All right, so now let's actually dive into this paper that actually drew some interesting conclusions about the relationship between kernel machines and neural networks, or more generally, models trained by gradient descent. And here's the link to the paper here. So mathematically, we can kind of think of a single neural network layer as a kernel machine, which actually uses something called the sigmoid kernel. So here we can think of this as sigma times W transpose X, where X is some input feature vector, W is the weights of a particular output into the next layer, and sigma is some nonlinearity, like a sigmoid function or a ReLU function. And this kernel function is really just this inner product right here. We can kind of think of each layer of a neural network as kind of the application of a kernel to obtain a specific output. So really, this is just sort of a looking at the actual definition of a single element in a single layer of a neural network as a kernel function. But sort of what's not really understood is that for multi-layer neural networks, there's really no known closed form kernel. If we compose kernel functions inside of kernel functions, like a multi-layer neural network does, there's really no easily interpretable closed form solution. So what was interesting about this paper is Domingo suggested that models, including neural networks, that are trained by gradient descent are approximately kernel machines through something that he called the path kernel. Now, before we kind of dive into this, gradient descent, at least as defined in this paper, is just this iterative process where we have some weights at time step s. And then to get the weights for the next time step, we basically subtract eta times the gradient of the weights with respect to some loss function L. So W sub s is the model weights, eta is the normalized, in this case, learning rate, and L of W is the loss function. So as the kernel for his approximating kernel machine, Dominguez proposed the path kernel, which essentially reproduces the output of a model Y trained by gradient descent in the limit as eta approaches 0 and the number of steps approaches infinity. And here it is. This is the path kernel. So we have a model Y sub W of X at a given time t during the training process with weights W of t for each time step t from 0 to capital T in the training period. This is sort of our kernel. Now, it looks kind of complicated, but we'll kind of dive into this equation and try to figure out what it means. So according to Dominguez's paper, the path kernel measures how similarly the model at 2 data points varies during learning. The more similar the variation for X sub A and X sub B, the higher the weight of X sub B in predicting Y. So it sort of predicts how similarly certain data points vary during the training process, if that makes sense.
This looks like it's only applicable for a single hidden layer. Am I missing something?
No, this is actually treating the entire, you can think of it as treating the neural network as kind of a black box with some computable gradient. So this kernel is computed over all training steps in the gradient descent algorithm, if that makes sense.
Okay, go ahead, please.
yeah, so it's sort of hacking into the gradient descent process and sort of using that to define the kernel function instead of the neural network explicitly, which is kind of interesting. So here's kind of a figure from the paper that sort of illustrates this. So if you can imagine, we have, let's say a set of data points, maybe x sub 1 and x sub 2, and those in conjunction form some gradient of the loss function, which is denoted by nabla w of y of x. We can kind of think of the weights of a model as traversing some path in a high-dimensional space. And what the path kernel does is it basically integrates over that path through the high-dimensional space and measures how similar would the weights evolve under a particular data point if we were to sort of wind back the clock and do the gradient descent process over with this new training example. So in the figure caption, it says, this is sort of how the path kernel measures similarity between examples. In this 2D illustration, the weights follow a path on the plane during training. The model's gradients for x, x1, and x2 vary along it. And the kernel is basically the integral of the dot product of these gradients over the path taken during training. Because on average, over the weight path, this inner product is greater than this inner product, y1 has more influence than y2 in predicting y, all else being equal. So our measure of similarity between elements in our data set and previously unseen elements is how much influence would a new data set or a data element have in the gradient descent process if we were to incorporate that and sort of retrain the model on this additional data point. So if you want all of the juicy details, you can dive into the paper. But essentially, this is sort of reverse engineering the gradient descent process to try to extract a kernel that gives us meaningful information about how influential particular data points are in the training process. So the form of this approximate kernel machine looks something that's essentially like a mathematical kernel machine, in the sense that we have this summation of sort of these alpha sub i's times our kernel function k, plus some bias term, which is essentially corresponds to our initial weights. But this isn't sort of a true kernel machine in the sense that this is sort of the limit as our learning rate approaches 0 and our number of training steps approaches infinity. So it's not really a true kernel machine, it's an approximate kernel machine. Another sort of key caveat is that these coefficients alpha sub I are actually dependent on the gradient descent process, and thus dependent on the actual x sub I that are used to train the model. So in a true kernel machine, these alpha sub i's are actually independent of any kind of training algorithm or any of the x sub i's that are part of the data set. So it's not a true kernel machine, but we can actually extract some meaningful insights here. So yeah, again, this is an approximate kernel machine, since in a true kernel machine, the alpha sub I are free parameters and not dependent on the x sub i's. So onto the significance of this result. This result is significant because it provides sort of an alternative perspective on neural networks and may be helpful in moving beyond sort of the current black box understanding of neural networks and how they function. So it's kind of commonly believed that neural networks are powerful because they sort of learn a locally optimal nonlinear representation of their input features. And part of that is kind of motivated by this idea of a kernel projecting some data into an infinite dimensional space in order to separate it linearly there. This work kind of seems to suggest that instead these models sort of learn nonlinear interpolations between training data, using sort of where those interpolations are sort of governed by the inner product defined in the path kernel. And this work also suggests that sort of support vectors exist during the training process and are discovered as the neural network is training. And this sort of implies that models trained by gradient descent essentially learn which training examples are more useful than others for discriminating between output values. And again, this sort of usefulness can be measured by these alpha sub I values. So one could picture if you could actually explicitly compute this path kernel and fit a kernel machine using this path kernel, you could figure out sort of which elements of the data set were actually useful in training the model and which ones were essentially just useless or redundant. So that's sort of the primary insight that the paper seemed to emphasize. So I'll go ahead and open up the floor to questions. Hopefully I didn't bore you too much.
Thank you very much, Colin. I was never a big fan of radial basis functions. It always reminded me of just nearest neighbor lookup, which I don't know if you're going to do nearest neighbor lookup. That seems to me to be a pretty quick thing. I guess the radial basis function allows you to not consider all the data, but still not really exciting. I don't know. I think some of the other kernels are a lot better. Well, I tell you what, we don't have a lot of time, so let's go ahead and move on. Again, if you have to jump off, feel free to jump off, and we will be posting this so you can watch it. So we'll go now to Ming Kun, who is going to give adversarial distribution training for robust deep learning. Ming Kun, it's all up to you.
If I'm not prepared today, yes, okay, I make it next time.
You're not prepared today.
Oh, yeah,
Okay.
I'm not prepared.
Well, let's talk. Trevor, are you ready?
Yeah, I can go.
Okay, Trevor, take her away, buddy.
Okay.
All right, can everyone see my screen? I can see about half of it. All right, let me try doing this real quick. Full screen now? Yes. Sweet. All right, so my presentation was on the implementation of a reinforcement learning algorithm with absolutely zero human knowledge. And this is based off of AlphaGo. And this specific AI was called AlphaGo 0. And I'm just going to, throughout this presentation, just call them by their secondary name so I don't have to repeat AlphaGo 47,000 times.
By the way, I would challenge the assumption of this title. And I want you to look at it as Trevor presents it and see if you believe that there was no human knowledge inserted into the AlphaGo problem. Because I don't agree with the title, but go ahead, Trevor.
All right, so first things first, some quick background. So obviously AlphaGo is the first computer program to beat a professional Go player and was trained using a combination of watching and copying human gameplay and then using the learning from the human gameplay and putting it through machine learning. The original AlphaGo used two deep neural networks, one that was entirely dedicated to move probability outputs, and another one for position evaluation. And that move probability neural network, like I said, was trained by supervised learning to predict human moves. These two neural networks were combined with a Monte Carlo tree search to narrow down the search to moves with higher priorities and to evaluate possible moves within said tree. And then another quick thing, this paper likes to use the phrase tabula rasa, I believe is the correct pronunciation, which is the theory that all knowledge comes from experience or perception. So going in, so some of the different AlphaGo versions that were used in the paper itself, FAN was a previously published program that played against one of the authors of this paper, actually Fan Hui, in 2015, and which was spread out across 176 GPUs. Lee, who defeated Lee Sedol in a 4-1 game in 2016, was previously unpublished, but it bore a lot of similarities to FAN. Some of the differences include Lee was trained on outcomes of fast games of self-play, which was their first steps towards a complete tabula rasa approach to zero. It used a convolutional approach, which I'll go into more detail a little bit later, and was distributed over 48 tensor processing units, otherwise known as TPUs, which enabled it to evaluate the neural networks faster. And then finally, Master was a program that defeated some of the top human Go players 60-0 back in 2017.
And it uses the same neural network architecture, the reinforcement learning algorithm, and the same Monte Carlo tree search algorithm as 0. However, some of the differences, AlphaGo Master used some of the same features and handcrafted rollouts as Lee and was initialized by supervised learning from human data. So the goal for this paper, they were trying to create an AI that will learn without any human involvement to demonstrate that quote unquote superhuman performance or professional performance can be achieved without human domain knowledge. This AI, which I will call 0, is trained purely by self-play reinforcement learning, only uses a single neural network and uses a simpler tree search without performing the full Monte Carlo rollouts and simulations. So obviously, AlphaGo 0 had to know how to play the game, despite given no human domain knowledge. So the 4 points of knowledge that 0 was given, 0 was provided perfect knowledge of the game rules, which was implemented in their tree searches. The games are terminated after both players pass or after 722 moves, which is the most amount of moves possible in a game of Go. 0 was also provided a set of legal moves in each position. 0 uses Trompe-Taylor scoring, which is a type of AlphaGo scoring rule set during its tree searches and self-play. The neural network architecture is matched to the 19 by 19 grid structure of the board for Go. And then another thing that 0 was told was that the rules are invariant depending on which way you look at the board. So either rotating it or reflecting it across itself. So the data sets have been augmented during training to include random rotations or reflections of each position to kind of supplement the training itself. So the algorithm, in this case, theta is going to stand for the input parameters and f theta represents the neural network. S, which is the input that the neural network takes, and it represents the raw board representation. So just looking at the board, the position, the history of the moves, and outputs 2 things. One, the move probabilities, which is a vector P, and a value V. Now, P is a vector of move probabilities. It's a probability of selecting a move A. So the probability is determined between A and the board representation.
So give me some examples of some of the parameters associated with this. Was it a convolutional neural network? What's the size of the Go grid that you start with? Do you know?
So the neural network is a 19 by 19 board, and then they also had a 17 deep neural network. I'm going to explain it a little bit more down the road. But
okay, but what's the size of the Go board?
19 by 19.
It is by 19 by 19. So that wasn't a window for the convolutional neural network then. So what are some of the parameters?
Well, the parameters are 8 previous moves in both the X and Y directions, and then the color of the tiles.
Okay, thank you.
Going back in, V was a scalar evaluation, which estimates the probability of the current player winning from the raw board representation, which is just a basic equation shown down below in that last line. So catching up to Dr. Mark's questions here, it was a input of a 19 by 19 by 17 image stack, such as 19 by 19 is the typical board for a game of Go. 17 represents 17 binary feature planes, 8 of which are X feature planes, 8 of which are Y feature planes, and then a singular color plane to signify the turns. 1 if it's black and 0 if it's white. The X feature indicates the presence of the current player's stones. So for example, it is a 1 if it is filled by the player's color at time step T, and it's a 0 if it's empty or if it's filled by an opponent's piece. And then the Y feature is just on the opposite for that, for the opponent's stones. And then there's 8 of them because in Go, you need to be playing with previous turns in mind. For example, repetitions in the game are forbidden. So there are 8 of them to represent the current turn and the 7 previous turns that the AI has taken. and then they're all concatenated to form that input S, or the raw representation of the board itself. So now this is going into the architecture of the neural network. They called it a tower, neural network tower. It was a single convolutional block followed by 19 residual blocks. This convolutional block was started out with 256 filters of a 3x3 kernel size. Next was some batch normalization, so it recenters and rescales the inputs in order to help the performance. And then a rectifier nonlinearity, which is the activation function in order to convolute it all. The residual blocks are almost a double of the convolutional block, so it follows the 256 filters, the batch normalization, the rectifier nonlinearity, followed by an additional 256, followed by another batch normalization. But then it also adds a skip connection to add the input to the block as sort of its sixth step before a final rectifier nonlinearity. So it has 7 features rather than the 3 that the convolutional block contains. And then it outputs into what they call heads. After the final residual block is outputted into 2 separate heads, one for move probability and one for value. The policy or the probability head is simply just 2 filters of a 1x1 kernel size, batch normalization, a rectifier, and then finally a fully connected linear layer that outputs a vector of size corresponding to the probability of all the intersections. So the size of the board, 19 by 19, which equals about 362. The value head follows similarly to the policy head or the probability head. Of 1 filter, 1x1 kernel size, batch normalization, rectifier, before fully connecting to a linear layer that connects to hidden 256 layers, another rectifier nonlinearity, and then finally a fully connected linear layer to a scalar, and then a 10H nonlinearity outputting a scalar in the range of -1 to 1. So just a brief summary of that architecture. So it's a total of 39 parametrized layers for the residual tower, an additional 2 for the policy head, and an additional 3 for the value head. This type of neural network, a 20-block residual tower, is known as dual res, which is the architecture that Zero used. The dual res architecture was tested and compared against 3 other types of architecture. A separated res, which is 2 separate towers, one tower outputting purely to the probability head and another tower outputting purely to the value head. A dual convolutional architecture, which is a non-residual tower of 12 convolutional blocks, followed by the probability and value head, and then a separate architecture, which are 2 towers of 12 convolutional blocks, with 1 tower following the probability and another tower following the value head.
What does SEP mean?
Separated. So in the dual, it is like 1 tower does both and then outputs to 2 separate heads. Well, as separated, you have an entire tower just for 1 head, an entire tower just for the other head. Does that answer your question, Dr. Marks? Cool. Okay. And then the separated convolutional architecture was the architecture used in Lee, which defeated Lee Sedol 4 to 1. So they compared the architectures they compared the 4 architectures based off of ELO rating. If you're unfamiliar with ELO rating, it is basically just a probability that one will win over the other. So you can see the graph A represents the ELO ratings based off the separate architectures used. You can see that the dual residual, which is this light purplish over here, has a much higher ELO rating than the separated convolutional architecture that Lee used. And then this was just players that were obtained with a combination of a trained network and AlphaGo Zero search. And then the B graph represents the prediction accuracy of professional human moves from a taken database. You can see again that although it wasn't the highest in terms of accuracy for predicting human moves, the dual residual tower architecture beat the separated convolutional architecture. So training, so 0 was trained purely through self-play. Each position, a Monte Carlo tree search is executed and outputs the probabilities of playing each move, which is denoted by pi. The tree search is guided by the neural network, and it tends to select stronger moves than just the pure selections provided by the neural networks, which is known typically as a policy improvement operator. Moves are selected by subtracting the A of t by pi of t, and t is just denoting the turn. And then the terminal position, or sub capital T, is scored using the game's rules to produce the game winner denoted by Z. So as you see a brief picture here, you can see that this has an empty small cutout of the board, goes through each tree search before determining the best move, pi 1. This is checked with the neural network's output. The move is
Okay,
taken here.
Trevor, I'm gonna have to take a quick 2-minute break. So just talk among yourselves. I'll be back.
Okay.
Anybody know any jokes?
What do you call a belt made of watches? A waste of time.
Oh no.
Yeah, it's like the joke about Orion's belt. I've heard it's only got a rating of about 3 stars.
Nice.
I'm gonna confess my brain's very fried.
Yeah, same here.
Oh,
Is
Trevor,
what's up, Sam?
sorry, I did have a question on one of the previous slides, the prediction probability.
Yeah.
That's of all possible moves. It predicted the correct one, that percentage. So it's not like a coin flip type thing. It's like you have a lot of options and you have to
Yes.
correct move. Okay. Well, because it was around 50%, so I wanted to make sure that it didn't seem like it would be a coin flip, but 50% is a lot more impressive when there's 35 options,
True.
whatever. Or probably more.
Anyone going to the championship game on Saturday?
The what now?
The football Big 12 championship game up in Arlington?
I might be sleeping. We'll see.
Fair.
I will be listening while furiously studying for exams next week.
It's fair. How bad your final schedule look like, Owen?
It's not bad. I just got a couple bad ones. They're like the ones where you have like your final exam, or like you have your final midterm and then your final exam.
Yeah,
So
that's rough.
yeah.
I am interested to see how the
Okay, Trevor, I'm back. So
welcome back, Dr. Marks.
thank you. Did you miss me?
Yes.
Okay, good. Okay, go ahead, please. Thank you for your patience.
Yeah. What was the last thing that you heard, Dr. Marks?
I need to take a 2-minute break.
Okay. Okay, so I'll just start over with
No,
this.
you were talking about, I think this is a what is a not a Monte Carlo, but a decision tree of some type that generates probabilities.
Yes. So it generates the probabilities of moves, checks it with the neural network, and then as each possible move continues down, it creates an entirely different search in order to generate these pi values. They're checked by the A values from the neural network before finally this S sub capital T is formed, which then decides the game winner Z. So this is just the neural graphic of the neural network that trains. So you can see each move is thrown through this tower of layers here and outputs both the probability pi as well as the scalar value V, which is then moved back up into pi1, which S2 goes down through the tree search, going down through this tower before generating this pi value, and then continuing on as each move goes through the game itself. So the Monte Carlo tree search, it operates in 4 distinct stages: select, expand / evaluate, backup, and play. Each edge of the tree search stores a probability P, a visit count N, a mean action value of Q, and a total action value of W. The goal of the search is to maximize an upper confidence bound Q plus U until a leaf node S prime is encountered. The leaf nodes are the ending values of the tree search, and this U value is inversely proportional to the probability P divided by 1 plus the visit count. And then the leaf node itself is expanded and evaluated only once by the network.
Okay, let me ask you this, Trevor. Is this probability computed and updated as the game plays, or is the game sort of fixed? And if you have a certain board geometry, that you're going to have this same probability?
No, so the probability changes as each move is played.
Well, I understand the probability changes, but if I have, say, a certain, let's see, this strikes me as a Markov process. So the next move is only a function of the current state of the board. So if I have a current state of the board now, and then I didn't do anything to my system, and I had that same board configuration, would it generate the same probabilities?
Well, Dr. Marks, he mentioned it has a 17 or a 8 move history window.
Yes.
So
Okay, well, let's say, okay.
But if
good-
it's all
good
the same,
point.
yeah,
So,
it's the
so
same
it is,
question.
yeah, no, you're exactly right. I was wrong. This is not a Markov sort of, well, it's a 7D Markov, whatever that is. But the point is if you had that same history, would it give that same probability structure?
I believe so. But the issue is in the game of Go, the only way to attribute the same structure on the board is by passing, which is basically just forfeiting your turn. And then the game is over if both players pass.
I think Dr. Marks's question is if you play 2 separate games,
Oh,
and in
okay.
one
Okay.
game you happen to have the same set of boards as in the other game, would it have the same result?
Yes.
That's probably the question.
Okay, thank you. Thank you.
Continuing on, this is just a diagram of the tree search. So as you can see, it's finding that upper confidence bound through each possible game move. So if black were to play to the right of its piece or up and to the right of this piece, and as it goes down, it moves on to the next stage where the probability and the value are selected before becoming down to a leaf node here. And this A through C is just continuously tested until the leaf node is expanded upon. It goes back through to determine the mean action value, and then finally the move is played. So this first stage begins at a root node S, that's supposed to be S sub 0, finishes when the current leaf node S of L at time step L, and it has to be when T is less than L. The action is selected at each time step using the argument max of the upper confidence bound, and it uses a variant of the predictor and upper confidence bound in a tree algorithm, as you can see by this equation here, with C sub BUCT is a constant that just determines the level of exploration. And this algorithm was also used in previous versions of AlphaGo itself. Continuing on to the second stage, that leaf node is added to the neural network evaluation. D sub I of P and V is equal to the neural network of D sub I of that leaf node S sub capital L. And that DI just represents a dihedral reflection and or rotation selected at random. So like I said, the board is, and the rules are invariant if the board is rotated or reflected. And so it's just a random reflection or rotation to the board in order to supplement the training. From there, the positions are evaluated by the neural network. Each edge value is initialized to 0 except for the chosen move, and then the value for V is then backed up. In the backup stage, the edge statistics are updated backwards passing through the tree. Visit counts are incremented by 1, and the action values are updated using these two equations below, with the total being just the previous total plus the value chosen V, and then the mean is the total divided by the visit count. And then virtual loss just ensures that each thread evaluates different nodes through this tree. So finally, in the final stage, 0 selects the move A to play in S sub 0, which is proportional to the exponentiated visit count, with this tau value being a temperature parameter that controls the level of exploration. The search tree is then reused at later time steps. The node that corresponds to the played action becomes the new base node or the root node S sub 0. The subtree, if it was explored, kept below the new S sub 0 is kept, as well as the statistics and values, and the rest of the tree is then discarded. And 0 resigns if the root value and the best node value are lower than a threshold value called just V resign. So how it trained itself, using the combination of the neural network and the tree searches, moves are played at each time step T. The game finishes when both players pass, when that V resign value is met, or when the game exceeds a maximum length. The game is then scored to give a reward of either a -1 or a +1. The data for each time step is stored, ST, pi t, and Z of t. And then Z of t is the plus or minus RT value of the game winner from the current perspective of the current player at that time step T. This data then trains the new network parameters, and the neural network is adjusted to minimize error between the predicted value V and the game winner Z, given by this loss equation here, with this value C just being a parameter to prevent overfitting. Training for what the first iteration of 0 took approximately 3 days, and this started completely random behavior, and continued without human intervention for 72 hours. In that 72-hour period, 4.9 million games of Go were played using 1,600 simulations for each tree search, which equates to about 0.4 seconds of thinking time per move. The parameters are updated from 700,000 mini batches of 2,048 positions using that dual res tower formation I described earlier. So as you see on the right is a nice little graph of that ELO rating that I mentioned earlier, over the training time. 0 is represented by this blue line here, and as you can see, it did not suffer any oscillations or forgetting of previous strategies, which was an issue in previous versions of AlphaGo. And in about 36 hours, 0 had already outperformed the previous iteration Lee. For comparison, Lee was trained over the course of several months, and within 36 hours, 0 already outperformed it by ELO rating. And then finally, once 0 was completely trained, it was tested against Lee in similar match conditions and time controls to the least at all match. 0 won 100 games to nothing against Lee. And 0 also only needed 4 tensor processing units compared to the 48 TPUs that Lee required. And those 48 were split over multiple machines. So as you can see, 0 vastly outperformed the previous iteration. It was then tested against a supervised learning neural network, purely just to predict moves made by experts or professional Go players, or what the paper calls superhuman. Although the supervised learning network was better at predicting professional human moves, 0 defeated the supervised network within the first 24 hours of training. This implies that 0 was using a strategy that was different from normal human play. It was developing its own strategy just from nothing. And so they sat there and were like, new strategies, how is this possible? So 0 began discovering these non-conventional strategies. I'm going to butcher these pronunciations, but it's professional Joseki, which are corner sequences for the board. Professional variants of these corner sequences began appearing in 0's play, including variants that were previously unknown or lost to Go players. Zero had rapidly progressed from random moves to understanding concepts of Go, including Tsuji, which are tactics, concept of life and death, capturing races, shape, influence, and territory in the game of Go itself. Now, Shicho, which is the ladder capture sequences, which is normally one of the first things that humans learn when they're being taught the game, was understood by Zero much later in the training. So that wasn't even the first strategy that Zero learned as it was beginning to teach itself the game of Go. So once this was initially decided, they decided to come up with Zero 2.0, which was just a basically restart of Zero using a larger neural network trained over a longer period of time. This time a 40 block tower, which is just that one convolutional block followed by the 39 residual blocks, was used rather than the 20 block tower. The second version of Zero started a completely random behavior and was trained for approximately 40 days. Over those 40 days, 29 million games were self-played. The parameters had started at about 3.1 million batches and were brought down from there. In order to test this, they were tested in an internal tournament against Fan, Lee, Master, several previous Go programs, and just a base raw network player, which was selecting moves purely on the maximum probability within Zero's raw neural network. And if you remember, I mentioned earlier that Monte Carlo tree search was choosing stronger moves than just the raw neural network probabilities themselves. So continuing on the results, tournament was scored using the ELO point range, like I described, where the difference in ratings serves as a predictor to the outcome of the match. For example, if there's a 100-point difference, that results in a 64% chance of the higher ELO point player to win, while a 200-point difference results in about a 75-76% chance of winning. On the ELO scale, Zero came in at a little over 5,000. Master came in at about 4,800. Lee came in at 3.7 thousand. Fan came at 3.1, and the raw neural network came at 3.015 thousand. Other Go programs didn't even reach the 2,000 point mark on the ELO scale, as seen in the bar graph here. You can see this raw neural network only came up to 3,000, and Zero in this case is the clear winner in the ELO rating. And you can see here on the left is the time of training and the ELO rating for Zero as it began making its way up and above the previous best iteration of AlphaGo, known as AlphaGo Master. And then finally, they decided to have a undisputed match between the two, between Zero and Master, in a 100-game head-to-head match with 2-hour time controls. Out of the 100 games, Zero won 89 times, while Master, who had previously beaten professional human players 60-0, only won 11 times. So the conclusion, this tabula rasa approach, the pure reinforcement learning approach, in challenging domains such as the game of Go or other board games such as chess, is a completely feasible approach. Is it possible to achieve a professional level of play without the guidance of human knowledge or without knowledge of the domain besides basic rules? In total, the training time for pure reinforcement learning is slightly lesser than previous versions, as we saw as the several months of Lee versus the 3 days of Zero, and achieves much better asymptotic performance when compared to human-guided data. Over the course of a few days, Zero was completely able to rediscover Go knowledge and produce novel strategies that can lead to new insights in one of the oldest board games. That was the end of my presentation.
Okay, thank you, Trevor. Yeah, clearly the AlphaGo is just an astonishing program.
Mm-hmm.
I have a colleague, and I want to get your impression on this. He says that if I'm playing AlphaGo,
Mm-hmm.
and the network is not being trained anymore, and you have access to this, for example, the probability of tree, okay? And I believe that the algorithm that's being used is a minimax sort of approach, which was proposed by Claude Shannon way back in the 1950s for winning at chess. What you do is you choose your move that minimizes the maximum damage. Is
Okay.
that what's happening here?
So personally, I'm not familiar with the rules of Go itself. I know chess, and damage can easily be applied to losing pieces, like valuable pieces. With Go, however, there were strategies in forming, like I was mentioning, corner sequences that were
Well,
just previously
it turns
unknown.
out that AI beat chess a long time before Go.
Yeah.
Go was the holy grail of AI, and it was astonishing when it happened. And since then, we know of other astonishing things that it's done. The thing that really blew my mind is that this AI could win at Texas Hold'em.
Really?
That's incredibly surprising to me. I thought Texas Hold'em was just a game of bluff. But if you look at these super contests, it's the same people that rise to the top and end up in the finals every year. So they got something going algorithmically. Yeah, and it won there. But here's my point. If you're not training AlphaGo anymore and you have access to, for example, this probability tree, and you always don't choose the maximum probability, and you build stacks which the neural network has not seen before, do you think that the game could be gamed if we knew that information in order to win?
I would believe so. I think the reason why this one was so successful is because it came up with strategies that were previously unknown. So if you had unknown strategies,
Yeah.
then it's possible, if you were no longer training the network, that you could outgame the game.
Yeah, obviously, I don't want to say definitively whether it would or would not, but it seems to me that my friend, who is a computer science specialist, has a little bit more insight than I do. He made this comment, and I thought, wow, that's very interesting. So if you knew what was going into and this is the idea, you know what's going on in the head of your opponent, and you can use that to game and to upset the strategy. So I don't know. It's an intriguing possibility. So anybody else? Colin, do you have any ideas? Matthew, what do you think?
I'm kind of curious what it would be like to see AlphaGo performing against a human player running just the raw neural network, using the policy and the value outputs as the actual moves. Because that seems a little bit closer to how a human actually plays.
I see.
They sort of have this internal representation of the game, but they're not really running Monte Carlo tree search in their head, considering multiple possibilities, probably more than 10 or so moves ahead.
Yeah.
Because they sort of built up this internal representation where if I make this move, I can sort of push somebody into this scenario that I've seen before and know how to win in. What would really impress me would be to see AlphaGo beat a human using just sort of the raw policy and value outputs from the neural networks without performing search.
Without doing the search, yeah.
There's
some people that looked at the output of AlphaGo and, the Texas Hold'em game, et cetera, and they said, this is going to be really great because we can use this AI, for example, as a decision-making CEO or a commander in a battlefield. I have some definitive comments on that, but or definitive ideas, but I just wondered, well, let me tell you what my thought was. In order to learn anything, it has to be forecast ergodic. In other words, the system cannot change with respect to time. If, for example, you had the game of Go and you change the rules, probably the program that was written to win would not work as well, or might even be totally dethroned. And so you play the same game by the same rules over and over and over and over again, 93 million times, I think you said, Trevor. And that access to the stationarity of the game is 100% required in order for the game to work. I would think that a CEO or a commander in a battlefield does not have that luxury. They are seeing scenarios which they have never seen before. And there is nothing that is, I'm referring to this as forecast ergodic. It is not a forecast ergodic sort of process, such as necessitated by the game of Go or the game of chess, where you have a stationarity and a time invariance, which goes on again and again and again, that you have to take advantage of. So anyway, that's my thought on that. So that's one of the weaknesses of this reinforcement learning, is that there is an underlying assumption of this stationarity and this ergodicity. And there's so many things in the real world that aren't stationary and ergodic. And I think is one of the reasons that DeepMind has been losing $500 million a year for the last 2 years, is that they're looking for some place for this to stick in industry. The place where I saw, which was really nice, was application of reinforcement learning to train robots to grab different elements off the assembly line. I'm not sure if you knew this, but Amazon, for example, has these little robots that go around the room and get packages off the shelf, and they bring it to a central station where human beings stick these things in a box, because the human doesn't have the ability to do that. But I've seen some work done in that using reinforcement learning, which I thought was pretty cool. And there is a sense of ergodicity there. You have the same problem again and again and again and again and again. Same sort of class of problems. So anyway, despite all of its grandeur, there is this ergodicity requirement for any problem that you reduce to practice. Okay, well, I think this is good. We've gone over, and there's 4 of us remaining. Okay, you guys get kudos for sticking around. So we will see you next time, and hopefully keep the presentations a little bit shorter. But anyway, I would have not have reduced the time of any of the presentations. They were all very excellent. So, okay, be of good cheer. Bye-bye.
Thank you.